And what about that? Okay. So hopefully I'm not hiding the, the thing. Excuse me. Okay. So we're going to spend a few sessions applying what we've been studying as far as these event graphs and listening and all that stuff goes to modeling movement. And we're going to take the simplest approach, which is to which in this case is to work in 2 dimensions. I know that in some of you are kind of learning all kinds of fancy things in 3 dimensions, but we're going to stick to 2 dimensions. And the so it's now in order to kind of be on the same page. I know everybody has had vector algebra in the past, but we just need to review it because that's going to be a big part of how we're going to be doing this. And then we'll move on to how to model it using this event idea, which is a little bit different than some of the other approaches. So, okay, so here's kind of the the summary of all the vector algebra that we're going to be using pretty much for the most part. The idea of a vector is in 2 dimensions. It's going to be a tuple. Sometimes they're called X and Y, but if we're going to go Z, X, Y, Z, but then when we go to 4 dimensions, etc. So regardless of what you call it, one is typically horizontal and the other is going to be vertical. So X1 in this case would be the location on the horizontal, and the other would be on the vertical. And so conceptually, we're thinking of a Euclidean plane like this, where we have horizontal, so a given point is going to be located in this 2-dimensional space. So now one of the things that we're going to be doing are adding 2 vectors together. And when we add 2 vectors together, we're going to add them component-wise. So if X were X1 and X2 and Y were Y1 and Y2, then the sum of the vectors is the sum of their respective components. And similarly, another thing we're going to do is multiply a vector by a scalar. So in this case, alpha is a scalar, X is a vector. And when we multiply a vector by a scalar, we simply multiply each of the individual components by that scalar. Okay, so and the inner product. Okay, now that's something that we are going to be exploiting, and there are a number of different ways of representing this. So, so when you think about the operations on vectors, again, we can add them, we can multiply by a scalar, but what does it mean to multiply 2 vectors together? There are at least kind of 2. There's the inner product, there's a so-called outer product, which we won't be using, but it turns out the inner product is something which is very useful. And the inner product, we multiply each of the respective components together and then add them. And you know, the inner product has another representation, which for our purposes is not going to be quite as useful, and that's involving the angle between the two vectors. So it's like the idea is that if I have, say, if I have another vector here, then the inner product it's actually related to the angle between the two vectors, as well as the magnitude of their respective of the two vectors. That's another way of representing it. It turns out that for the kind of computations we'll be doing, the algebraic one is a little more useful. And that can be applied to the idea of a norm, or the length of a vector. And one way of characterizing it, just for all dimensions, is the square root of the inner product of the vector with itself. Or in Euclidean space, it would be the Euclidean, how does that joke go about the square and the hippopotamuses and the square and the other two, something like that. Anyway, so Pythagoras. And then the final thing that we will actually use is the idea of a unit vector. So if I have a vector has a location, another way of thinking of it, it's got a sort of it's got a magnitude. And so if so the magnitude is what we're also calling another word for the norm. So that's how long this vector is. And sometimes we want a unit vector, that is a vector whose length is exactly 1, but it's pointing in the same direction as that vector. And the way to do that is to take the norm and then divide the vector by its norm. We haven't defined divide, but it's really that's the same as 1 over the norm times, in this case would be x1 and x2. Is it rather than calling them x and y? I mean, one of the reasons for this is that we'll be dealing with different vector, different labels for vectors, and so it's just more convenient to kind of do it that way. Anyway, so this is this should all be review. You've all seen this before. Has anybody not seen this before?
Sir, I have a simple question.
Okay, just a second. I need to. Okay, go ahead.
This might be a dumb question, but like in vector algebra, like I'm more used to seeing vectors as in like x1, y1. Is it a convention in discrete event simulation to have like only differentiate it by the numbers like x1, x2, and then y1, y2, like that?
No, it's just my convention, because see, like here, when I'm adding vectors x and y, so how would you call the vector y? Yeah, it's a convention. I mean, if 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 x and y, I mean, if that's more comfortable for you, fine. It just for me, this is kind of the main motivation of it, and here as well. In other words, to denote the elements of a vector by its name with the subscript. The other reason is that that extends well to arbitrary dimensions. So if we're not going to go to 4 dimensions, but it's quite possible to be working in 4 dimensions, and then and if you're working in n dimensions, then the subscript idea is kind of more useful. But it's not a hard and fast rule. That's just me. Okay, so what's our basic problem? So let's reduce the problem that just down to its most basic form. So I want to model things that move around in a two-dimensional world. And so what are the elements of that? I mean, the basic element of that, of the things that kind of move around, is kind of basically one maneuver. So if I have a unit which is located at x naught, say a vector in 2D, and that, let's just say that at time 0, it starts moving to a certain destination D with a constant velocity v. And this is what we want to simulate. Now, kind of the other thing that's going to come up is the difference between velocity and speed. And this is a reminder that velocity is a vector and speed is a scalar. And the relationship is that the speed is the norm of the vector of the velocity vector. So if I'm saying I want to move along this vector at this velocity, then that's, the velocity has both magnitude and direction. So that's what we want to model. Now, the usual way of doing this, and if you've seen models that do this, is something called a time step. And you've probably heard me allude to the fact that this is not the way we're going to do it. But it's important to kind of understand why, what some of the issues are with the time step approach, and how the discrete event approach at least overcomes those issues. Of course, every modeling approach has its issues, but the question is picking your poison. Okay, but the time step approach is we have a certain time step, and we'll call it, say, delta t. And every delta t, the way to do this using a time step approach is every delta t we would advance by delta t times the velocity vector to that location. So if we had the same information, so we're starting at x naught, we're moving to this destination at a given velocity. So here's the first time step, we go here. The next time step, we jump over and go here, and then etc. So now the idea of this is that if we want to move to a particular destination, we just kind of hop along like this with our time units, and then after a certain number of these time steps, we reach our destination. And the thing, there are a lot of there are situations where a process is inherently time step. One example is animation. When you look at an animation or a movie or a video, what you are seeing is in fact an optical illusion. It's basically fooling your brain by displaying a series of still images, one after the other, with a certain amount of time in between each one. And it basically fools our brain into thinking that that one image moves into the other. I mean, our brain, basically animation is an illusion. I mean, what we're really seeing, is a series of still images presented to each other, and it would look something like this. And so you might be thinking, okay, what's the problem with this? What's the issue? Well, the issue is that for a given model, this time step is set by the system. It's set by the simulation that you're using. And here's what can go wrong, is that if the size of the time step relative to where you're trying to go, if for example we had a slightly different time step and performing exactly the same thing, we go here, another step, and then all of a sudden, when we take the last step, we've overshot our mark. And this is not a vacuous thing. This happens. This happens in actual models. And so, you know, again, this is the most simple, in the most simple, most basic thing, there's already a problem with approaching it with the time step. Now, there are a couple of how should I say, it's like you know, people kind of really, for some reason, some people are just very, very resistant to the idea of leaving time step as a method. And so what they, you know, I know one application, one agent-based model that displayed this problem. And so they went back, and the fix was when it overstepped the mark, it would then kind of try to adjust. It would try to take a step back. So it said, and then when it worked perfectly, it would actually step back like that. The problem is that trying to do this just for every possible movement situation is rather challenging. So in fact, what they would what would happen, and this was actually a real situation where it would stay, the step back would actually be a little too big, and then it would take another step and then miss again, and then maybe go a few times and then hit. And there were situations where it literally got stuck. It literally got stuck, vacillating back and forth and never actually hitting the mark. This proved to be a problem in the particular scenario that was being developed, because the agent in this case really needed to reach this destination at a particular point in order to do something. And the thing is, it never got there. It literally never got there. So the and in other situations, this has this also has kind of a name. I don't know. Have you heard the term bullet through the paper? You know, like the idea is, say this is a piece of paper and you're firing a bullet at that paper, and we're trying to simulate that. And what they found was that with sort of a naive time step, what would happen is the bullet would kind of go like this, and then emerge on the other side of the paper without having gone through the paper. And so they came up with a term, a bullet through the paper problem. And the fixes they had were very similar to what they had here. So it's like, you know, if you have a methodology, and for doing the most basic maneuver, you need to kind of do a fix, then there's kind of a little bit of an issue. Okay, so this is what not to do, or at least in my, and you know, but just by the by, and I won't harangue too much, I hope. I mean, it turns out that this is only the tip of the iceberg. It turns out that in time step models, in very many situations, the size of the time step actually affects the results. Sometimes only quantitatively, and sometimes qualitatively. That is, that I have personally seen at least one or two studies in which the conclusions based upon a time step model were actually totally incorrect. And they were based upon this, they were kind of based on this skipping thing. What was happening was that there were sensors that were supposed, you know, they were, I forget whether they're UAFs or helicopters, or, but they were patrolling, and they were supposed to be detecting the bad guys. And what would happen is, because of this phenomenon, what would happen is occasionally bad guys would actually step over the sensor's range, whereas if they had been going continuously, they would have been detected. But because they were able to kind of leap over it in a similar manner as making it to the other side of the paper, that basically they were these kind of leakers attacking the high value target, and the simulation indicated that this would be a problem. And it turned out that when you did it right, it wasn't a problem for that. So the point is that this isn't a vacuous thing. This is a real thing. Okay, so let's, but this isn't a time step course. This is a course in discrete event. So how can we do this in such a way that that is consistent with the kind of things that we've been talking about? So what are the events? So the thing is that we want to define events in such a way that our target destination is reached at exactly the right place at exactly the right time. So again, our basic data are, we have an initial location, we have a velocity, and then, we have a destination that we're trying to reach. Now here's the thing, notice that here, the trajectory is actually continuous. Now, as opposed to this, which is an event graph component, a piece of an event graph. So there's nothing in between these. In the event graph, the idea is that we have an event that we start moving, and then we have another event that we are end moving. And what this is this is the time that it takes to traverse from our location to our destination at the given velocity. And let me say that again. Given all the information we have here, the event graph piece that represents this is we have a start move event, we have an end move event, and then what we need to know is what is the delay between when we start this move and we end our move, which will be exactly at our destination. Well, so when I say exactly, I mean the only inexact thing when we implement this is the inexact nature of double precision of floating point arithmetic on a computer. I mean, that's the only inaccuracy. I mean, we do not have anything like this where we actually sort of miss the thing. In other words, if I actually kind of do this, and then at this end move event, my unit is located exactly where it needs to be at exactly the right time it was. Now, what you're probably thinking is that thinking of now understand that this arrow here is not like this arrow here. This is, if we're traveling in a straight line, I mean, this is actually, our unit is physically moving along this line here. And here, we're not moving along any line. Here, we have scheduled an event on the event list, the end move event, which is going to occur TM time units later. However, here's the interesting thing, is that for some reason, if I were to stop the simulation and we're only here, or I mean, let's say, that's wrong. Let's erase all this stuff. So let's say if I wanted to stop after a certain amount of time, so let's say after a certain amount of time has elapsed, then where would I be? I would be here. I would be at my initial point plus the amount of time that it's elapsed times my velocity vector. I know exactly what that is. And so I want, for any arbitrary time in between, I want to know, I want to know what that location is, because I mean, that you're probably thinking that, because just in its basic form, what this does is at one point in time, my unit is located at the starting point, and then all of a sudden, sometime later, boom, it's like it transports to the destination. And of course, that's not how things actually work. So we want to make sure that that's not what's happening. So, and the reason, and it turns out, again, especially, this is after sort of many arguments with various people who are kind of trying to defend time step with all of their might. It turns out that it's sort of the Sherlock Holmes principle, which is, I don't know, you can ask your great-grandparents about who Sherlock Holmes was, but although not the Robert Downey version, I mean, the kind of original ones. Basically, it was like, if if you've eliminated all possibilities except for one, then that one, no matter how unlikely, is the answer. So here's the thing: is that remember what is the primary rule of the discrete event state? What do the state trajectories of a discrete event model look like? They are piecewise constant. In other words, they look like this over time. But here, the trajectory of the unit that I'm modeling is actually moving continuously in time. So what that says is that the location of the unit cannot be a discrete event state. It simply cannot. You know, why? Like if I'm, you know, if I'm looking at this if we kind of look down as if this were up the plane. Okay, here I am, and I'm kind of moving continuously. So this trajectory cannot be a state. In other words, the location, the unit is in continuous motion during the move. Location is continuously changing, and so therefore location cannot be a discrete event state. And so maybe you're thinking, well, if location can't be a discrete event state, then we can't do it. Well, not so fast. So let's build a model here. Okay, so remember, our model consists of parameters, state variables, and an event graph. So the parameters that I'm gonna have is an initial location. I'm gonna call it xi. So it's like when we start, when we fire up our scenario, our unit is going to be located at a particular place. And that, you know, where is it located? Well, we need to tell it. And that's going to be a parameter, because that's going to be its initial state. It's going to be a vector. And remember, parameters don't change throughout the replication, a given run. And so the initial location, even though the actual location is going to be changing, the initial location is not. I mean, if I started off at this point, then that's where I started. And then the second is going to be, excuse me, a speed. Okay, why a speed, not a velocity? Well, I mean, typically that's just the way it's characterized. I mean, what is the maximum, you know, how fast can this thing go? And in our, obviously in a more complicated model, we're going to have we're going to be going at different speeds at different times. However, remember the principle of starting as simple as possible. And one of the other reasons why that's important is that if we start at this very, very simple model, and suppose for some reason we hit a roadblock that, okay, we just can't go any further, then there's no hope in doing a more complex situation. But okay, so those are our parameters. So now our state variables, I'm going to kind of sort of consistent with last, I'm going to call it x naught, which is the location of the last stop point. And that's initially going to be our initial point. So the last place where we stopped, that's an I, that's a capital I, is going to be our location. And then sometime later, if we're going to stop at another location, then that's going to be another state. It turns out we need to know when our current move was begun. And that's initially going to be zero. We're going to say it's 0 initially, you know, just. Okay, now our current velocity. And remember, velocity is a vector. And our current velocity, see, the reason why we define speed is that we're always going to be moving at a constant speed in this model. Again, that's something we can modify later when things get a little more complicated, and we can and we do, and we may not do it this quarter, but it can be done and has been done. Okay, but the thing is, the velocity is going, that's a state, because that's going to be changing. Like, certainly if we're moving, our velocity is zero, and this zero is a vector. Now, just in terms of notation, I don't, you've probably seen notation where you put like a little arrow or somehow denote a vector. That, well, for whatever reason, that's sort of a pain. I don't like doing it. I mean, it's just, it's not that I don't like it, it's a pain to keep doing it. So, and what I found is that in context, you should be able to tell what a scalar is and what a vector is. And then finally, since we're going to be moving to just different destinations, which may change, and so I'm going to call it my current destination. And initially, I'm going to say that's null because I don't have a destination yet. Okay. So these are my discrete event states. But then remember when we were talking about queues, when we were modeling our basic multiple server queue using only the number in the queue and the number of available servers, we saw that we could, using those two states and our parameter, the total number of servers, we could derive another state, we called it L, which were the total number in the system. And that is an implicit or derived state. Now, in that particular case, L, the total number in the system, was also a discrete event state. But we can define another, in this case, we can define an implicit state, which is not a discrete event state, and that's our location. Remember, we said location cannot be a discrete event state, but it can be an implicit state. And the reason is that we're not explicitly representing this, but if you ask a unit that starts moving at a location x naught, at time t naught, with a velocity of v, and at time t, I say, where are you? Then using our discrete event states, we can say exactly where we are. So in other words, the location at any given time can be determined from the discrete event states. And so it's not a discrete event state, the current location, but it's an implicit state, meaning that using only discrete event states, we can compute it at any time. And this has an interesting property in that, unlike a time step, like if we look at our time step, in a time step model, the state of your system only exists at these discrete time points. I cannot even ask this system, where are you at this time, if that time is such that they're in between. In other words, I can only query the objects in a time step simulation at a multiple of the time step, and in between, where is it? And so in a time step model, the thing actually literally jumps from one place to the next. So it's like a short range transporter, basically. And so the interesting thing about that is that the discrete event approach to this is more continuous than the time step approach. So I hope you're getting that. All right, so that's our stuff. So here's our simplest mover, and so rather than null, actually I define there is no such thing in Java, but I did define one in SimKit, NAP, which is not a point, and not a point is a point. In other words, a vector whose coordinates are not a number. Okay, so here's our simplest mover, and so we have a run event, as we always have, in which we initialize our state variables. So the current time is 0. Our last stop location is our initial location. our velocity is 0, and our destination is not a point because we don't really have one. Okay, so now, and as you can see, this is a fairly simple event graph, but with a few complicated state transitions in between. So let's take a look at kind of what is going on here. So here's an event, move to E. So what is E? E is the place I want you to move to. So when the event move to E is this actually occurs, then my unit is going to well, remember now what these event graph models do is they do what the state transitions say they do, not what the words say. And so when I say move to this, what am I going to do? I'm going to set my destination, my current destination, to that location that was passed in as an argument. And you know, just to kind of keep things as simple as possible, I just have it scheduling a start move event. It turns out that well, so what does start move do? Well, if it's well named, that means that, okay, now we're going to actually start moving. And so so how do we figure that out? Well, the first thing we need is our velocity. And so what is our velocity? So let's unpack this this expression here. So D is our current destination. X0, that's the place where we're sitting. This is our where we last stopped. So we're stopped at this location, and we're now saying we're going to move to this destination. So so let me, I'll put it over here. So we're sitting here, and here's our destination. But remember, we wanted to know what our velocity is going to be. And all we know is our speed. We know our speed, and we know these three things. So what can we do? Well, the first thing is, what is the vector between x0 and D? It is D minus x0. That's the vector that's drawn here. Now, what I want is I want a vector in that same direction, but with a speed equal to the speed that I'm going to go. And so to do that, I'm going to turn this vector into a unit vector. How do you turn a vector into a unit vector? You divide by its norm. So the norm, and this would be a Euclidean distance here. I divide my distance, my vector from my location to my destination by the unit vector, and this now is a unit vector, but pointing in the right direction. But I want the magnitude needs to be the speed. So then when I multiply it by the speed, then I have a velocity vector that's pointing in the right direction and has the right magnitude. In other words, the magnitude of the velocity vector as it was constructed is exactly equal to the speed. Okay, so so we have our velocity. Now, since whenever this event occurs, that's going to be the time that I start moving, and I need that in order to do this calculation here. So I'm going to set my my time I started moving to the current sim time, because I can always, remember, sim time is a global variable in event graph methodology. And then finally, I need to know what the delay is between when I start and when I end. And what is that? Well, how far am I traveling? Well, I'm traveling at, this is this norm of this vector. This is how far I'm traveling. And how long does it take you if I travel a particular distance at a particular speed? How do you compute that? You divide the distance by the speed, and that gives us the delay between when I start moving and when I end move. And then when I finish moving, I basically now my last stop is my destination that I was going to. My velocity is 0 because we'll say we're going to be pausing, and now I don't have a destination anymore. So I'll set that to be not a point. And here you just need to be careful to do this before this. So. Okay, so is it clear? I mean, what's remarkable to me is that this simple event graph does what we're trying to do. In other words, what we're trying to do is model a situation where we perform one maneuver by going from one location to the next. And now all I need to do, now how do I notice that this is a component? So this is why it's important to know what sort of listening, sim event listening is about. Why? Because if I just run this component as it is without anything else, my run method will execute, I'll initialize my state variables, and then nothing else is going to happen. So what do I need to do in order to trigger this? I'm going to do that today. That might have to wait till tomorrow. But, okay, now the implementation. First, I'm going to talk about Java. I don't have a slide for the Python one. That's my bad. But there is a corresponding one. But okay, now in Java, Java has a point2D class, which is turns out to be a lot better, a lot more useful than their old point class. It's got a weird construction. So point2D is actually an abstract class, if you remember what an abstract class is, and it has two concrete implementations, point2D float and point2D double. Now, if those of you who were in my class last time remember my harangues against floats. Basically, floats are, if we're doing any serious computations, floats are an abomination. So we'll always be using double arithmetic. So point2D double is a concrete class with double value coordinates. There is another one, point2D float, which is a concrete class with float coordinates, which the problem is that floats just aren't, they don't have enough accuracy at all. Okay, and then points, for a point, I can get the X coordinate, I can get the Y coordinate, they come back as doubles. I can set its location to another point. This turns out to be a very useful property. So instead of having to instantiate all kinds of new points, if I, for example, in this one, where we set our last location to our destination, all I need to do is set location on my my last location, last stop location variable. Or I can set them directly by X's and Y's. I can do that. It does have a clone method. It returns a copy, but it's not implemented very nicely. We typically have to cast it to a point2D. So sometimes that is necessary, but okay. So basically we've kind of done that there, but then okay, now what about, okay, when we look at this event graph, it really doesn't do it's not going to do a whole lot. So we need to make it do something, and this is okay, what kind of why do things this way? Well, because it's once we have the ability to move to do one of these maneuvers, to go from one location to the next, then we can put those together in different ways in more complex more complex rules. And so the idea of movement is having simple maneuvers based on a rule. And the concept here is what I call a mover manager. And it's a component which is going to direct a single mover according to its rule. And I put rule in quotes because there's almost no limit to what these rules can be. We'll look at some of the simplest ones. So the simplest one is what I call a path mover manager. And that consists of a list of waypoints. And the idea is that the mover in question is going to visit each waypoint in sequence and then stop at the end. In other words, if I have a certain number of points and and kind of the final one, and if I start here, then it's going to go here and then here and then here, here, and then here, and then stop. And then a simple extension that is what I call a patrol mover manager. And so what the patrol mover manager is something like, so let's say I had a bunch of points here and I did a path mover manager, I would stop at the end, but for the patrol, basically instead of stopping, I go back to the very first place and I keep going around and around until somebody says stop. so stopping those is kind of the issue. And then this is mostly useful for the random mover manager is one where, okay, we don't have a preset sequence of paths, but we have a random, at each point we generate a random destination and we say go there, and then when it gets there we generate another one, et cetera, et cetera. Okay, so let's see, I think I have time to look at the path mover. So here's a path mover manager. It directs a single mover and its parameters would be a path, which I'm going to have is going to be, in this case, I can have a two-dimensional array. I could have that as a list as well. But arrays are simple. And then just for kind of, it turns out a Boolean that says start on run. In other words, in certain situations, I want to start that at a particular, either at a particular time or when a particular event occurs. But for testing purposes, sometimes I just want to start right away. So that Boolean's there. Now our state variable, in this case, since we're moving along the path, the next index is going to be the index of the next destination that I have. And for some reason, I initialize it to -1 just to make sure that until you actually start doing this, you're going to get exceptions, and that's kind of baked in. And then the next waypoint is initially not a point. So the event graph, interestingly, looks like this. So here, our run initializes our values, and then here's this is the reason for the start on run. So it's like I can either unconditionally do that, in which case it would always be doing it, but or this way I can either do it at the beginning or not. Okay, so let's kind of look at these events. So I have an event next waypoint. So what's the next waypoint? Well, I'm going to add 1 to my index. So when I do that first, it's going from here, it's going to go from -1 to 1. That's kind of why it was -1. And then my destination is going to be my path, the path at that index. And now I'm going to schedule a move to passing this this location to the move to event. And so this is what when I hook it up to the list as a, now this is actually a dangerous thing to do, but if you're really careful, then it works. So let's see what's going on here. Here is my simplest mover. It's listening to my simplest path mover manager and vice versa. So what's going to happen here? So here's a run. And let's say start on run is true. We're going to identify the next path or the next waypoint. Schedule a move to passing the destination as its argument. That will then be heard. So now the next waypoint was actually heard by the simplest mover, but it didn't have one, so it just ignored it. But move to, this has a move to with that the right argument. And so it schedules this, and then sometime later, this end move will occur. And when that end move occurs, that's going to be heard by my path mover manager here. And when I hear that, if my index is less than the length -1, okay, remember the off by 1 thing, then I can schedule a next waypoint. And so now At the next one, I is going to be, for the second waypoint, the index is going to be 1. I pick off the destination associated with that. I schedule a move to, the move to gets heard here. It keeps going until the end move was at the last waypoint. This becomes false. Next waypoint does not get scheduled. End of story. Okay, so I'm a little bit over time here. So if there are no questions, if I'm feeling better tomorrow, it'll be in class in the morning. If I'm not, they'll both be on Zoom. I'll send an announcement to let you know. And if there are no questions, we will adjourn.